Hello, I'm Katie Amaral, and in this video, I'll be showing my final project for the Harvard Extension Large Language Models class. This project is a Retrieval Augmented Generation search system for medical research question answering. AI has the potential to significantly improve healthcare outcomes by enhancing medical research and care. Large language models can accelerate research by allowing clinicians to search across large data sets to find accurate information very quickly. Large language models, however, are imperfect, occasionally hallucinating and providing factual inaccuracies while all sounding confident. In healthcare, even a small percentage of hallucinations is unacceptable due to the high consequence. The goal of this project is to improve the accuracy of LLM responses for medical question answering by grounding the context in verified medical research data. This project implements a RAG search system to search the PubMedQA dataset and generate answers based on medical research data. This technique is very helpful in improving the accuracy and therefore trustworthiness of the LLM responses. This project shows that RAG is able to ground responses in verified medical research contexts. The dataset is PubMedQA, a biomedical Q&A database created from PubMed text. This dataset is available on Hugging Face with an open source MIT license. The full dataset has 211,000 records with 1,000 records annotated by subject matter experts. The data schema has an ID, a question, research context, a long description, and a final answer. This project loads the subset with 1,000 records that are annotated by subject matter experts. The 1,000 records are split into training and testing sets with an 80-20 split. The PubMedBERT model is an open source embedding model that is fine-tuned on BERT for the specialized use case of biomedical terminology. This model has been evaluated on the PubMedQA dataset and achieved a 93.27 Pearson R-score. The LLM chosen for this project is Claude Haiku 4.5 with the Anthropic API. This model has 90% of the performance of Claude Sonnet 3.5 with lower cost. This model has 73.3% accuracy on the SWE bench verified benchmark. That's the software engineering verified benchmark. For the RAG architecture, the user's question is embedded and compared to the testing data in the vector database with semantic search and the cosine similarity algorithm. The top scoring results are added to the prompt for the LLM to ground its response in the relevant context. A single call is made to the LLM with the user's question and the retrieved medical research context from the vector database. The approach is the chain of thought pattern, where the LLM reviews the context, thinks through the answer, explains it, and then generates the final answer. The LLM is prompted to return responses as a JSON object with the explanation and the answer either yes, no, or maybe. Fast API is an API that generates the vector embeddings and ingests the data into the vector database. The Fast API search route also runs retrieval search to answer questions. The Fast API framework was chosen because of its asynchronous I/O capabilities, and since it's written in Python, that provides direct integrations with the most popular AI ML packages. Qdrant, or I should say Qdrant, is an open source vector database that supports similarity search. This database option was chosen for this project for its simplicity. The database is configured for cosine similarity search. And really quick, I'm going to switch over to the app to quickly show a demo. So as you can see in this screen here, this is the Fast API documentation endpoint. Fast API comes packaged with a tool called Swagger, which automatically documents the API endpoints. This is not something that you would want to use in production, but it's great for development. So as you can see, I've got a few API routes here, and the one we're going to be using is called ask. And this is where we ask the question. In this case, I'm asking, is colon cancer on the rise among young people? And I've already executed this search just in the interest of time. And this is the response that I get from the API. So I've got my question, and I've got the answer, which is yes, and the explanation. The LLM generated this explanation of the answer as well. And it's pretty straightforward. It says the text explicitly states in its opening sentence, the incidence of colorectal cancer in young patients is increasing. And it also provides the retrieved examples that were retrieved using the vector search. So I can see how it's grounding its answers. So I can see right here where it got its answer from, and it is grounded and based on research. So that's a pretty straightforward question, and additional questions might have the answer no, or might have the answer maybe, and it'll explain why I came up with that answer. So switching over to Qdrant, Qdrant has a dashboard where you can browse the data, and Qdrant has a concept called points. This is very similar to documents in a document store such as Elasticsearch. So here, as you can see, the points that were ingested into the vector database. We've got the JSON payload, and we also have the vector with 768 dimensions, since that's the dimensionality of the embedding model that we're using. It's also interesting, I can do basic filtering and searching, but I can also open up this graph interface, and I can see similar points on this graph. So yeah, very interesting tools, very lightweight, easy to use, and easy to set up locally. All right, switching back to the presentation. So now I'll talk about classification metrics. So the system has around 75.5% accuracy with 151 out of 200 correct answers on the test data set. The test set was held out from the training set. So those are the 200 test examples. And as you can see, there are some gaps in performance between the classification answers, yes, no, and maybe. The yes classification has the strongest recall and F1. The no classification has pretty similar scores with higher precision, but lower recall and F1 scores. However, as you can see, the maybe classification is very low, and it only has around 10% scores only. In fact, that's lower than it would be for random guessing. I suspect that this issue is largely due to class imbalance with the maybe answers in the training set. The maybe answers are a very, very small percentage of the data set, and right around 10% of the data set. So that means that there are fewer maybe answers for the few shot prompt, and it's unlikely to see any maybe examples in the prompt. I tried a few things to fix this. I tried increasing the number of examples in the prompt from 3 to 5 with the aim of maybe retrieving more of those maybe results, although that didn't seem to make a difference. I think one way, and the best way to fix this, is to significantly increase the size of the training set. Another possible improvement could be to implement retrieval with class balancing to make sure that there are, in fact, maybe examples in the few shot prompt, although there could be some limitations with that if there just aren't very many maybe examples that are relevant to the question. All right, and then this next slide, as you can see, I created a heat map for the confusion matrix where it's showing the actual answers versus the predicted answers. And next, I'm going to talk about the cosine similarity scores. So the cosine similarity scores here compare the explanation generated by the LLM with the verified long answer that was annotated by the subject matter experts. So the texts are embedded with the PubMedBERT embedding model and compared to each other with the cosine similarity algorithm. This is actually a very simple implementation using the Hugging Face sentence transformer to create the embeddings and PyTorch to run the cosine similarity function. The average score, right around 0.74, shows a fairly strong similarity. The standard deviation is small, indicating that the scores are close together, which shows that the system is consistent. There are some outliers. There were 3 scores below 0.5, and the minimum score is 0.28. While the maximum score is right around 0.92, which indicates that that instance is a very close match to the expert opinion. So this proves that, generally speaking, the RAG system is able to ground the LLM responses in the verified context. And the full cosine similarity scores can be found in the eval results directory of the project. All right, so the strengths for this project, it seemed that the specialized fine-tuned embedding model worked pretty well to retrieve relevant results from the data set whenever they were available. The few-shot approach also worked well to give the LLM examples of the expected format of their response. And the chain of thought approach worked well to generate the long explanation and the answer itself. The LLM consistently returned the response in the desired JSON format with the required keys to distinguish between the answer and the explanation. And overall, the RAG approach seems to successfully ground its responses in the verified data when that context was available related to the question. And that gets us into the limitations. So the biggest limitation of this system is that the data set is relatively small, with only 1,000 examples annotated by experts. Of course, the training data set is 800 records. That means it's a relatively small data set in which to search for answers to questions. So with that limited coverage, there's only a small scope of questions that could be potentially answered successfully. Although it still does demonstrate the architecture and capability and could be expanded to a larger data set by ingesting the full 211,000 records. However, most of those are not yet annotated by experts. For responsible use with any type of LLM system, even with RAG enabled, it might be susceptible to inaccuracies. So if this is ever deployed in production, it should be made clear that this is a research tool only and should not be used as a replacement for medical advice. All right, thank you so much for watching, and let me know if there are any questions.